Hello everyone and welcome to our next session of our Digital V-Days. So I'm very happy to introduce into the next topic. My name is Markus Eberle and I will moderate this webinar. And yeah, I welcome you to the topic Next Generation of Self-Heating Definition Performance Rated Current. And yeah, our speaker today is Alexander Lang. Hi Alex.
Hi.
Nice to have you here.
Thank you.
And yeah, he will do the presentation today and also answer your questions at the end of the presentation. So you can just ask us all your questions within the chat, and then after the presentation we will go through them. Then if we can't answer all your questions within this live webinar now, we will answer them later on via email. And yeah, for now, I think that's enough from my side. I wish you an exciting webinar, and yeah, Alex, have fun.
Thank you very much, Markus. So also welcome from my side. Thanks for having me here today. I'm Alexander Lang and I'm working as a product manager in the position of a technical lead at eiSos in the Power Magnetics team. And today I want to show you something regarding self-heating and how we name the self-heating in the last months, which is then defined as performance rated current. Good. So, like said, self-heating. Here I just brought a data sheet of one of our components, the WLQS, and where in this specification can we find the parameter of self-heating. This is mentioned in the area of the electrical properties, so let's zoom in a bit. And there for sure you can see several kinds of specifications, and then one of these specifications is then linked to an heat difference. So we have a delta in the temperature, and this delta is here, for example, defined with 40 Kelvin different. These 40 kelvins are linked to a current, and in this example close to 6 amps. So this means our rated current, our self-heating, which is called rated current, is linked to a specific DC current, which is running through our component and causes a heating. And this heating is then about this 40 Kelvin. Good. So, like mentioned, I'm working in the team of Power Magnetics. We are mainly handling power inductors for DC-DC converters. So these are single coil components, mainly consists out of one winding with an input and an output, and then a specific core design around to get a good performance for the application. So like said, or like showed in the previous slide, the self-heating is linked somehow to a current. So this means power inductors are used in DC-DC converters. So there's a power inside of the which is put into the component, and then also a power which is lead out of the component. And in the meantime, there are some losses because we are using winding, which is mainly out of, or which is normally out of copper, and this for sure has some resistance, and that is why we have losses. In a DC-DC converter, power inductors have to face two kinds of losses. These are the DC and the AC losses. But to make things easy, we will skip now, for now, the AC losses. We will talk about this later, and we will focus on the DC ones. And like already mentioned, power loss equation is pretty simple. Maybe you notice from your studying times that it's just the I square R formula. So this means depending on your current which you move through the component, and depending on your RDC, the power losses are rising. So this means what we expect as a self-heating characteristic as a self-heating curve from the component. We expect a quadratic function. So let's have a look again inside of the data sheet. And what we can see here, the self-heating of a component is like expected, this quadratic function. So this means if we let a DC current through our component, the current will heat up accordingly. So how to read this chart? Like said, or like showed in the beginning, we have our 40 Kelvin temp rise, and then we go horizontal until we meet the line, and then we go vertically down, and then we read where we are on the current axis, and this is how the rated current is defined so far. So this was just one example of a definition of one of our components we have in our portfolio. Now I want to give you a bit of market situation. So how are others defining this kind of value? And there I brought you some examples. So for instance, here we have IRMS with 20 degrees C and a 40 degrees C rise without any further mentioning or specifications. Then there is also iTemp as a typical value, and again a 40 degrees C rise. Then there are also rated current definitions with a 15 Kelvin rise. So this means the temp rise itself can be also differ. Another example is that we have again two temperature rises, 40 degrees C and 100 degrees C, but this time in combination with the time, so after 1 hour. So the time is mentioned here, first one. And also what is mentioned here is that the temperature is measured on the surface. So the surface temperature is 45 degrees C. And then also another example where we can see that the rated current is in relation to the saturation current. So we have a definition of the inductance drop, which is then a saturation effect, and then also a temperature rise with 25 and 40 degrees C, which is then again a heating specification. And then also here a value which is called approximately, so it's again a reference value, let's say like that. And last but not least, again a specification where it's just mentioned that the temperature will rise 40 degrees C. So what I want to show here is that there are many kinds of specifications in the market, and this could lead to the conclusion that comparing rated current values only based on the data sheet could be quite a challenge. But let's go on. Or last one here, that either the rated or the saturation current could be the limit, which is totally fine, but again, it's a different kind of specification. Good. So let's go a bit into the detail of the power losses. So how are they generated and how are they distributed, and how do we get from the losses to the heating? So again, we are on the formula P equals I square R, and then have a look on the RDC, where is this coming from? So we have a conductor, like said, it's on power inductors, it's for 99% copper. So this means we have our copper as a specific material constant, and then we have the length of the wire and the area of the wire. You can influence the area, for example, by using different kinds. So there's flat wire, round wire, Litz wire. So the area is different, even if the diameter can be different. And so you can increase the packing density inside of the component. Or for example, if you change the inductance value, you want to have a high value. So this means you need more turns. More turns means a longer wire, and that's why also the RDC is going up. So this means the RDC is mainly depending on the design of my power inductor, and whatever you're able to do, you can then fine-tune this parameter accordingly. Good. So we know now that the wire contains the RDC, so this means this is also our source where the heat is generated. So the current is moving over the copper wire, and because there is RDC, there is a loss factor, and this is where the heat is generated. But how is the heat distributed? So there are two kinds of ways. So one is for sure that the wire is transferring the heat to the core of the component, and then from the core surface, the heat is distributed into the ambient. This is highly dependent on the design. So for example, on the left side, we have some molded components. This means the iron composite particles are around the wire. So we have a very good thermal, or we have a very low thermal resistance between wire and core. So this means energy can be easily transferred into the material, and then the surface of the material can distribute the temperature into the ambient. On the other hand, we have pretty huge components where the winding is more or less just put on top or is assembled into the core. So we have here a shaped one, and there the wire is also distributing the heat directly into the ambient, or also distributing the heat onto the core, and then the core is then again distributing it. But because the winding only have punctual contact with the core, for sure the main temperature is transferred from the wire directly into the air. So this means based on the design, you can influence your thermal resistance between winding and core material, but once this is fixed, there is pretty little you can do. What else is there? Like said, power inductors are single coil power inductors, so we have one input and one output. And for sure, all inductors are sooner or later mounted onto the PCB. And there we have two kinds of connection possibilities. The one is THT and the other is SMT. But there the things are getting interesting, because if I have a pretty big area where I can connect my part onto the PCB, and then I can put a pretty big cover plane on that connection area, then things can get interesting. And this is what I want to show you here. So again, on the left side, we have always the same component, but what is different is the PCB below the component. So this means if I have a PCB with a small copper trace where I connect the part, then I can distribute less heat from the winding to the PCB. And as a consequence, my component is heating up faster. And this is then the black curve, like you can see here. So the 40 kelvins, temp rise is reached at about 15 to 16 amps. If I use the same component and just using a way more bigger PCB, or let's say copper plane below the PCB, then I can increase this value from, let's say, 16 amps to more than 30 amps. And again, we are still using the same component. So this means the rated current value can be highly influenced by the used PCB. So this means the measurement setup is a crucial factor for the definition of that value. So then, now we know that we can, or that there are many ways how we can influence it. So let's check again the market situation. How is this currently defined in the data sheets? And then here we have a pretty good example. It's already mentioned you should solder it on a PCB, and you have a copper plane, you have a copper thickness, and everything is already quite defined. But how to say, it's in first idea, but some details are still missing. But anyways, let's go on. Another one is here that we can read, okay, it's 155 degrees, it's not allowed to be warmer. But then also the definition starts here that everything can be influenced by tray size, thickness, airflow, and other cooling properties. And that is why temp parameter should be verified in the end application. So this means it's already the first statement that yes, it's a value, but please recheck it if this value is matching with your application at the end. Then again here, pretty plain explanation. So just rated current, 40K self-heating, and that's all. Here again, another description of how the setup is be, but then again, pretty similar explanation like here. Verify it in your end application. And then also here, without any further description of the PCB, and again, verified it in the end application. So, what are the current weak points of a specification? there are many ways to influence the final result. So a proper definition of how the value is measured would be appreciated, but it's not there. And it's pretty hard to make a relation between different kinds of components. So this means this value in the datasheet can be used as a first indicator, but more or less always needs to be verified in the end application. So this means if you're in the very beginning and you want to choose, let's say, the top 3 components which suits best for your application, it's very hard to compare the components based on the datasheet parameters. So the question is, how can we improve this? And this is where I want to introduce the IEC standard 62024-2, because this standard is classifying or is, let's say, defining how to measure the rated current, and it's also classifying in 4 different kinds of PCBs you can use for that measurement. And everything is well defined here. So this means lengths, widths, heights, how to connect, and everything can be read in the standard, and also the trace thickness. So this means whatever you need, you can find in this standard described quite well. So how have we used the standard for our definition? So this means we were now moving from the rated current into the performance rated current, and everything which is named now performance rated current is automatically linked to this IEC standard. And we have defined internally, so WE have defined internally to use these 3 kinds of classes. So class B for product series with standard requirements, class C for products which have a high packing density, and then class D for products which have current capabilities of 30 amps or higher. I will show you now some examples how this could look like. So example 1 for class B is the WEPD. And then you can see here performance rated current is defined, and also with a highlight on 1. And then you can see here below here, it's referred to the IEC standard. And then even a bit lower, you can then also see that this measurement has been done with a class B PCB. So it's well traceable how this value has been generated. And an example for class D. So it's an LHMI. This is a molded component, which is again normally used in high packing density applications. And then again here we have the performance rated current, and then also mention that this is measured now with the class C PCB. And then you can also see here's the thickness of the cover trays and so on and so forth. So if you are interested in details, you can get all of them. And then last but not least, class D. One example is here for the HCM, which is mainly used for server applications. So this means low voltages but very high currents, and like you can see here, it has a current of almost 64 amps, and that is why we have chosen for this particular series then the class D, which has then a thickness of 1000 micrometers or 1 millimeter. So this means with that one, we made it very transparent how this rated current value or performance rated current value, how we like to name it nowadays, has been defined or has been measured. Good. So as an overview page, whoops, this was too fast. As an overview for that one, some of our products have rated current and performance rated current now. The rated current comes from the VE legacy. So this means this is a PCB board where we have used for all of our measurements we did in the past. So this means we made an internal standardization. But again, only an internal standardization doesn't make, or is by this, it's very hard to compare with other products in the market. And that's why we say, okay, we will now also show the performance rated current, and this will be then for new series only the performance rated current will be shown from now on, and then with the proper class B, C or D specification. Yeah. And if you want to have further informations, we also have an app node. The number of the app node is down here, where the IEC standard is a bit more described, and then also the measuring methods. Good. So conclusion as the IEC standard. With the standard, we can offer the service of a very high traceability or transparency, how the value has been generated, how the value has been measured, which with kind of setup. And this means series can be compared on a defined level. So this means I really now see both have been specified with class D. This value is higher. So this means there will be a lower self-heating on my end application. And then also there's a better appraisal for the end application. So this means I know now, okay, this value has been defined with this kind of setup. I have a different setup on my end application. So this means the expectation is that the rated current value or performance rated current value in the data sheet will be different to the self-heating in my end application. But I'm very aware of this from the very beginning. Good. And then for sure, high trust in the value of the data sheet, because, you know, it's everything defined in the standard. Good. Going to one of these points. So now we have a pretty nice defined value, but in most of the cases, this value will be different to the end application build up. And that is why I want to introduce the rated current calculator, which is now available in the Red Expert. And this is the one below here. And the idea behind this tool is to, again, get a good statement regarding what will be the self-heating in my end application. So this means I can type in here the dimensions of my PCB, and then I will get a result of how the rated current will change. So let's have a more detailed look into that. Standard definition is the class C, so with 80 millimeters length, 40 millimeter width, and 105 micrometers. And then you can see the rated current like it is defined in the datasheet. So it's also class C in the datasheet, is matching with this calculated value here. So this means everything is working quite nice. But if I now change these values below here, then I will see, okay, if I only have 10 millimeters of width and 35 micrometers of cover thickness, and also a shorter length, then my value will drop from approximately 3 amps to approximately 2 amps. So this means if I'm a very early stage of designing my component or designing my applications, and I know exactly what kind of currents I will have, then this is the tool which will provide you the service if this component will at the end meet your requirements. So you don't have to test it, you don't have to wait until everything is built up, you can simulate it right away. Good. So as a short summary, we talked about where the rated current is coming. We focused on the DC. We focused on the DC losses, where they are generated, and how the rated current value then can be influenced. But one thing is still missing, what I also mentioned in the very beginning. So now DC losses are so far now defined, but our parts are used in DC-DC converters. So this means also there are AC losses. And there I just want to highlight one tool we have already for some years, and which is our DC-DC converter loss tool in the Red Expert. And with that one, we then have the full overview regarding all of the losses. So this means our tool, which is simulating the AC losses. You have again here your DC-DC converter and all of the specifications, and then you just type in what will be your input, your output, your current, your switching frequency, your duty cycle, and so on and so forth. And then as a result, you're also getting then the AC losses. So AC losses is something we are offering since years, let's say it like this. So then conclusion of definition of performance rated current overall. By using the IEC standard, we have a method to compare values very easily. So it's not necessary to read the fine print at the end of the data sheet. So just check what is the classification, what kind of classification has been used, and then it can be very easily compared. And then also by offering the new rated current calculation tool, this value, so if you're then chosen for a component, you can then simulate what will be the expected self-heating in your end application. And then also by offering the already existing DC-DC losses, you also have a statement regarding AC losses. And as a summary, so the self-heating of a component can be simulated in all kinds of complexity. Yeah. So this means comparing data sheet values up to the expected self-heating in the end application is now pretty easy to handle. And with this slide, I also want to close my presentation. I want to say thank you for your attention, and that's it for now.
Alexander, thank you very much for your presentation. Yeah, we already got some questions, and so hopefully you enjoyed it as well. So, but before we start into the questions, I would quickly share also the handout, so you can just download the slides you just saw. So now you should be able, and yeah, I see the clicks are coming in. Okay, but then let's start. We still have some time left. So I think we start with this one. Alex, will the IEC standard be used for all WE or Würth Elektronik components?
Currently, we have the definition that it will be used for all power magnetics. For the other products in our portfolio, for sure, we offer the standard, we offer our knowledge, and if other colleagues and departments will decide to use the standard, they are very welcome to do this. It totally makes sense for the power inductors, because here the losses are one key factor for the choosing of the right component. And yeah, that is why we use it here, but all others are welcome to also use it.
Okay, thank you very much. Then let's go on with the next one. So hopefully I will spell it right. Is the IEC 62242 class taken into account in the Red Expert graphs? And if there are multiple inductors selected for comparison?
Okay, so regarding Red Expert graphs, it is taken, so in the rated current calculator, it is definitely. And for all data sheets where we have this performance rated current, then also this performance rated current with the specific classification is then also mentioned in Red Expert. Yeah.
Okay.
Did I miss something?
I don't think so.
Okay.
Otherwise, then just please contact us again. And yeah, so also if there are any questions left after our webinar, then just email us at digital-v-days@we-online.com. Okay, but now next question, Alex, in reference to performance rated current for the Class D specifications, what does PCB couple width refer to? Is it the trace plane width connected to component you are referring to?
So Class D more or less says you need a PCB which have a certain length and a certain width, but the thickness of the PCB needs to be 1 millimeter of copper. So this is a quite interesting measurement setup, but anyways, it's working, and it's working quite nice. Yeah. And then again, the trace, the plane width, we are always soldering the component then on top of this PCB, or let's say on this copper planes, and then they have a certain length, and then on the other side, for sure, we connect then with cables to our current source. So we need a current circuit, so this means we have a power supply, then we connect with the cables to the PCB, and then from the PCB to the component. So this is how the measurement setup is generated, or how it is built up. And then how the PCB is built up, this is then defined in the standard, and we are following the definitions in the standard.
Okay, thank you very much. Okay, then we go on with the next question. Why is class A not used for measurement?
The class A, so class B, C, and D, there's only one PCB available. So this means this is well defined. For class A, you have several definitions. So it is more or less cut down into certain current ratings. So for example, there's a PCB for 1 amp, for 2, for 3, for 5, for 7 amps, and so on and so forth. And if we have a part which is, let's say, at a limit of 2 of these PCBs, there is already the chance that we get 2 values for one part. So just an example, we are using a 5 amp PCB and a 3 amp PCB. So with the 5 amp PCB, the rated current will be 3.1 amps, and with the 3 amp PCB, it will be 2.9. So again, both values would be valid, but it's not really, we don't have one value for that. If we're using class B, C, or D, everything is well defined, and there is no discussion why we've used this and why we've used that. And that's why we said, okay, to make things clear, we do not use class A and focus on the other classes.
Okay, thank you very much.
Welcome.
Then we are done with this question. Hopefully, you got all your answers, but I think so. Then we go on with the next question. Yeah, connecting large pads to switching inductors is contrary to good EMC practices. How does this balance out in the end?
That's a good question. So here I want to point out that on the rated current, we are focused on the DC losses. And that is why, by focusing on the DC losses, we can totally exclude AC stuff, and then also the EMC issues which could happen there. Again, the target of the IEC standard is to have a proper definition how the self-heating is defined, how the DC self-heating is defined. And that is why we are also offering this rated current calculator, because we are well aware that this standard is not often used in real case applications. Yeah. So again, we want to be transparent. We want to say this is how we are specifying things. But we also want to say, hey, we are aware that you are not using this, or you mainly will not use this in your end application. And that is why we have an additional calculator where you then can say, hey, if this is your trace, your rated current will be like following.
Okay, thank you very much. So I think with this, hopefully you can work. Then let's go on with the next question I see right now. I think that's also the last question for now. Maybe some more questions will come up. Alex, how to get from simulated AC losses to AC loss related heating on top of DC loss related heating?
Mm-hmm. This is one of our next steps we are doing. So currently we have our tool for AC losses, where we put again our part on a defined PCB and then doing our measurements with this defined PCB, and then we get AC and DC losses. So, and also like mentioned, we also now have our rated current calculator. So this means that we also get a result for DC losses. For the AC and DC one, we also then get a total self-heating of the component. And now we have our rated current calculator, where it just gives a statement regarding DC losses. So the next step will be to integrate this rated current calculator into the DC-DC calculator. So we are aware of that. This needs to be done. It will take some time until this will be implemented, but yes, this will come in the near future. That, you can then type in what will be your end application trace design, and then also with the AC losses and the rated current calculation assumption, then you have a total value of how your self-heating of the component will be.
Okay, Alexander, thank you very much. So these were all your questions for now. If there are any questions left, then just email us. And for now, then I say thank you also for your attention. Stay tuned with our Digital V-Days. And yeah, have a good day. Bye.
Bye-bye.